Welcome to Foundation Mathematics, Set Theory, Venn Diagrams, Unions, Intersections, Subsets, and Cardinality. The objectives for this session are to describe sets mathematically using set notation, describe sets graphically using Venn diagrams, manipulate sets by using unions, intersections, and complements, determine when a set is a subset of another, describe a universal set, given the universal set, form the complement of a set, deal with three or more sets in set theory, and specify the cardinality of sets and subsets. We're going to begin with the definition of a set. In mathematics, a set is the mathematical model for a collection of different things. It contains elements. These can be mathematical objects of any kind. For example, numbers, symbols, points in space, lines, other geometrical shapes, variables, or even other sets. Sets are usually named using a capital letter, and elements are put in curly brackets. So, for example, if F is the set of all fruit being served for dessert at my friend's dinner party, then F equals, curly bracket open, bananas, cherries, mangoes, curly bracket closed. Let's now take a look at another example. If A is the set of whole numbers between 1 and 5 inclusive, then A equals, in curly brackets, 1, 2, 3, 4, and 5. And another example. If B is the set of all odd numbers between 14 and 30 inclusive, then B equals the set of numbers shown on your screen. And now for some notation. Suppose that A is a set and N is an element in A, then in notation we write this as N is a member of A using the symbol shown on your screen. So in our example, we have 19 is a member of A. Elements of a set are never repeated. So for example, suppose that the set L consists of all the letters in the word Antarctica. Then we would have that L equals A, N, T, R, C, and I. We would not write this as L equals all of these letters in Antarctica with the A's repeated, the C's repeated, and the T's repeated. A Venn diagram is an illustration using circles to show relationships among things or finite groups of things. Overlapping circles have a commonality, where circles that do not overlap do not share those traits. And a universal set E is a special set including all the possible elements you will need in a given situation. So here's an example. E. At the moment, there's nothing in it. A set within the universal set, as shown here, can be represented by a circle. We could have multiple sets, so another set, B for example here. Let's take a look at an example. Place the following shapes in the correct region in the Venn diagram below. We have a set of shapes and a Venn diagram with two circles, one for three-sided shapes and one for blue shapes. Then we have the universal set, which encompasses all of these and includes all shapes which are neither three-sided nor blue. So let's proceed. The yellow rectangle doesn't fit into either of these two circles, so it goes outside them but inside the universal set. Similarly, for this green rhombus and the purple circle. However, the blue arrow goes inside the blue shape section, as does the blue pentagon. This triangle goes in the three-sided shapes, but of course isn't blue. And this blue triangle goes in both the circles. And finally, this parallelogram is neither three-sided nor blue. We are now going to look at some very special regions in Venn diagrams. So for example, this region, shaded here, represents A union B, represented by this symbol U. Let's take a look at an example to illustrate this. Suppose we have A, B and the universal set as shown. We are required to state the members of A union B. Here we have that A union B equals this set here. Here are all the set of values in A. And here are the set in B. Notice that 3 occurs in both, but is only represented once in the set. We've now put the set of numbers in order of size to make it easier to read. We will now look at A intersect B, which is this region here, and is represented by the symbol shown. Let's take a look at an example. If we have A, B, and the universal set as shown, and if we're required to find A intersect B, then A intersect B equals 3, because this is the only element that occurs in both A and B. We will now take a look at the complement of a set. This shaded region represents E without A. It is written as A to the power C or A dash. Let's take a look at this in more detail. Suppose E is the universal set and A is a set in E. Then we have A to the power C or A complement, denoting the set of elements in E which are not in A. So for example, if E equals this universal set, and A equals 3, 6 and 9, then A complement equals all the elements which are in E but not in A, as shown here. Let's take a look at another example. Suppose A equals 1, 2, 3, 4, 8 and 12, and B equals 3, 5 and 9. We also have that the universal set represents these numbers as shown on your screen. We are required to state the members of A dash. Here we have that A dash equals 5, 9 and 10. The numbers in red highlight the numbers in A. So the numbers which remain in the universal set are those which are in A dash. And now for the region B not A, which is represented by this shaded area and written as B backslash A. Let's take a look at an example. Suppose A, B and the universal set are as shown. We are required to state the members of B not A. A and B have only one element in common, and that is 3 as highlighted. Therefore, B not A is equal to 5, 9. What about A not B? This is represented by the shaded region shown. In this example, A not B is equal to 1, 2, 4, 8 and 12. Again, 3 is the only element which is common to both sets. Therefore, A is the remainder of the elements in A as shown. So in our example, we have B not A equals 5 and 9, and A not B equals 1, 2, 4, 8 and 12. So we can conclude that B not A and A not B are not necessarily equal, and therefore difference in set theory is not commutative. We're now going to take a look at disjoint sets. The empty set is the set consisting of no elements at all. It is also sometimes called the null set. Two sets satisfying this are called disjoint sets. If there is no intersection between the two sets, the circles do not overlap. Here, in this example, A intersect B equals the empty brackets as shown, which is equal to the empty set symbol as shown. An example of this could be positive odd numbers and positive even numbers. Here we have that A intersect B equals the empty set. We will now take a look at an example which combines several concepts together. Pause the video and have a go. Press play when you're ready to view the solutions. Let's take a look at part A first. We have that A equals the set of numbers shown, and B equals the factors of 20 excluding 20, and the universal set equals x in the natural numbers such that x is less than or equal to 15. We are required to write down the members of A intersect B and illustrate this in a Venn diagram. So let's solve this. So we have the set A as shown. B, the factors of 20, is equal to the set of numbers 1, 2, 4, 5 and 10. The universal set, which consists of the natural numbers x such that x is less than or equal to 15. So the universal set is the set of whole numbers from 1 to 15 inclusive. We are required to write down the members of A intersect B, or A and B. Let's begin by producing a Venn diagram to help us. So let's start with what's common to both sets, A and B. The number 1, the number 2, and the number 4. Nothing else seems to be common. And now for part B. We are required to write down the members of A union B complement, which is the set of elements not in A or B. So let's find what's in A. We've already covered 1, 2, 4, which is in A. So the rest of the elements are 3, 8 and 12. So we put those in A, but not in A intersect B. We now consider set B. The elements 1, 2 and 4 are in set B and A, and we've already considered those. and only 5 and 10 are left. So we add those to the set B as well, but they're not in A. So what's left? What's in the universal set which is not in A or B? We remove 1, 2, 3, 4, 5, 8, 10, and 12. So these have all been already taken account of. And what's left is 6, 7, 9, 11, 13, 14, and 15. And so the set of numbers A union B complement is equal to 6, 7, 9, 11, 13, 14, and 15, as shown. We will now take a look at subsets and supersets. A set A is a subset of a set B if all the elements of A are also elements of B. This can be illustrated as shown. Another example is if A equals 3, 6, 9 and B equals all multiples of 3, then A is a subset of B, since 3, 6, 9 are also multiples of 3. In notation, we would write this as A is contained in B if X is a member of A implies X is a member of B. Conversely, we can describe a superset as follows. A set B is a superset of a set A if all the elements of A are also elements of B. We can use the same example to illustrate this as well. And in notation, we would write this as B is a superset of A if X is a member of A implies X is a member of B. Now let's take a look at identical sets. The order in which elements of a set are written is not important, as we mentioned earlier. So sets with the same elements are identical. So for example, if A equals 3, 6, and 9, and B equals 6, 9, and 3, then A is identical to B. So if A is contained in B and B is contained in A, then A equals B. Now that we have some symbols, notation, and structure in set theory, we can start to define numbers using sets. We know that the most basic form of numbers would probably be the counting numbers, so 1, 2, 3, and so on. These are called the natural numbers. Notice that when we add two natural numbers, we obtain another natural number. So addition is closed over the natural numbers. Similarly, multiplication is also closed over the natural numbers, since when we multiply two natural numbers, we get another natural number. However, if we subtract two natural numbers, we could get a negative number, which is of course not a natural number. So subtraction is not closed over the natural numbers. We will therefore add a layer of complexity to our natural numbers. We're going to consider the integers. These are whole numbers which are negative or positive or 0. Notice that the natural numbers are contained in the integers. We also have that addition, subtraction, and multiplication are all closed over the integers. However, what about division? Dividing two integers may not give us another integer. So division is not closed over the integers. And so we add another layer of complexity, the rational numbers. These represent numbers of the form p over q, where p and q are both natural numbers or integers, and of course q is not equal to 0, as shown here. In notation, we would write this as the set of x such that, notice that the colon represents such that, x equals p over q, where p and q are both members of the integers, and q does not equal 0. Notice that the integers are contained in the rational numbers. But we also know that the naturals are contained in the integers, and therefore the naturals are contained in the rationals. Now let's take a look at the real numbers. The real numbers are the irrationals and rationals. Irrational numbers are numbers with infinitely non-recurring decimals. So the irrationals can be represented by q complement, or everything which is not rational. We also have that the naturals are contained in the integers, are contained in the rationals, are contained in the reals. And we also have that the reals are closed under addition, subtraction, multiplication, and division. What about square rooting? For example, what if we consider square root of -1? This would now be the universal set, or this square root of -1 would be included in the universal set and is denoted by this special letter C for complex numbers. Complex numbers take the form a plus ib, where a and b are in the real numbers and where I is equal to square root of -1. And we have this notation here now, or this fact. The naturals are contained in the integers, are contained in the rationals, are contained in the reals, are contained in the complex numbers. And so we've set up our number system. So let's summarize this. Remember, we began with the natural numbers, 1, 2, 3, and so on. We added on the integers, so for example, -3, -2, -1, 0, 1, 2, 3, and so on, in the negative and the positive direction. Then the rational numbers, numbers of the form p over q. Then the reals, which included irrationals and rationals. And finally the complex numbers, which would encompass the universal set. In arithmetic, the order in which we carry out operations is important. So, in the expression 3 times 5 plus 1, we carry out multiplication first. If we did addition first, the answer would be different and incorrect. If we wanted to do addition first, we would need to add brackets, as shown here. So in particular, we have that 3 times 5 plus 1 is not the same as 3 times, and in brackets, 5 plus 1. In set theory, when we are working with more than 2 sets, order of operations is also important. Let's take a look at an example. We have the universal set E as shown, and the sets A, B and C as defined, and we're required to find A union B union C and A intersect B intersect C, and then illustrate these in a Venn diagram. So let's solve this. We begin with our raw Venn diagram as shown on the screen, and then start to put the figures in. We should begin right from the center, or where all 3 sets intersect. Here. The only element which is common to all 3 is 6. Now let's take a look at intersections 2 sets at a time. Let's consider A and B first. The elements which are in A, which are also in B, are 2, 4 and 6. We've already considered 6, so we need to place the 2 and the 4 in the area representing A intersect B, but not in C. Now let's consider A and C. Elements common to both are 3 and 6. We've already considered 6, so we need to place the 3 in the region representing A and C, which is not in B. And now for B and C. The only element common to both is 6, so we don't need to add anything else to our diagram. Now let's consider each set individually. A consists of all the whole numbers from 1 to 6. We've already considered 2, 4, 6 and 3. What's left? Only 1 and 5 are left. So we need to add these to the set A, but ensure that they're not included in the regions representing B or C. So we place 1 here and 5 here. And now for the set B. It seems that all the set elements for set B have already been considered, 2, 4 and 6, and there's nothing left to consider. And similarly for set C. Now let's take a look at the universal set. This is all the elements from 1 to 7, or rather all the whole numbers from 1 to 7. We've already considered all the whole numbers 1 to 6. Only 7 is left, and so we need to add that to our diagram. This goes in the universal set as shown, but it's not in any of the sets A, B or C. The shaded area represents A union B union C. So all the elements, or whole numbers, from 1 to 6 inclusive, as shown. This shaded region represents A intersect B intersect C, which is only the element 6 in this example. Now we take a look at an example which illustrates that order of operations is important in set theory. Consider the universal set as defined and the sets D, E and F as defined on your screen. Can you find D union E intersect F, do you obtain the same answer if you carry out the union first or the intersection first? Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve this. If we carry out union first in D union E intersect F, we have D union E equals 1, 2, 3 union 2, 4, 5, which is equal to 1, 2, 3, 4 and 5. Let's now intersect this with F. To give us 1, 2 and 5. So we have that D union E intersect F equals 1, 2 and 5. But if we carry out intersection first in D union E intersect F, we have E intersect F equals 2, 4, 5 intersected with 1, 2 and 5 to give us 2, 5, since 2 and 5 are common to both sets. Now let's union this with D to give 1, 2, 3 union 2, 5. And this gives us 1, 2, 3 and 5. Therefore, D union E intersect F equals 1, 2, 3 and 5. Let's now take a look at both our results side by side and illustrate them in Venn diagrams. First, let's consider D union E then intersect F. This is our Venn diagram. And this shaded region represents 1, 2 and 5, or D union E intersected with F. The result on the right-hand side, in other words, D union E intersect F, is represented by the shaded region in the diagram on the right. Notice that the shaded regions are different, and therefore we can conclude that order of operations is important in set theory. We now take a look at the cardinality of sets. The cardinality of a set is the number of elements in a set. For example, if P equals C, A, R and T, then the cardinality of P is 4. So mod P in notation equals 4. Let's take a look at another example. Let Q and R be defined as shown. Find the cardinality of Q, R and Q union R. Let's solve this. We have mod Q equals 4, or the cardinality of Q equals 4, and mod R equals 3. Since Q union R equals 1, 2, 3, 4 and 5, we have that the number of elements in Q union R, or its cardinality, is equal to 5. Notice that mod q plus mod r equals 7, 4 plus 3. Therefore, mod q union r is not equal to mod q plus mod r, since of course 5 is not equal to 7. On the right-hand side, we've added the elements 2 and 4 2 times, since both of these elements are common to q and r. The inclusion-exclusion law gives a relationship between the cardinalities of q union r, q, r, and q intersect r, namely that the cardinality of q union r equals the cardinality of q plus the cardinality of r minus the cardinality of q intersect r. Let's apply this to an example. In a science college, all the students either study maths or physics or both. If the number of students studying maths is 335, and the number of students studying physics is 120, and the number of students studying both maths and physics is 33, then how many students are there in the college? Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve this. Let M be the set of students who take maths, and let P be the set of students who take physics. We have that the cardinality of M equals 335, the cardinality of P equals 120, and the cardinality of M intersect P equals 33. By the inclusion-exclusion law, we have that mod M union P equals mod M plus mod P minus mod M intersect P. So plugging in the values gives us 335 plus 120 minus 33 equals mod M union P. And calculating this gives us that the number of students in the college is 422. So here's the inclusion-exclusion law for two sets, as we've just discussed. The inclusion-exclusion law for three sets is more complicated, as shown on your screen. And you can imagine that this law is going to be even more complicated for four sets. For three sets, we also have these associative laws. So order of operations is not important for intersection when we're intersecting throughout, or unioning when we're unioning throughout. We also have these distributive laws. A union B intersect C equals A union B intersect A union C. And similarly in the line below. This brings us to the end of this session. If you have understood its contents, you should be able to describe sets mathematically and graphically using set notation and Venn diagrams, manipulate sets by using unions, intersections and complements, determine when a set is a subset of another, describe a universal set, given the universal set, form the complement of a set, deal with three or more sets in set theory, and specify the cardinality of sets and subsets. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.